In the previous lectures, we have discussed Borel's 0-1 law and also Borel-Cantelli lemma. Now we are going to mention or state another similar kind of result, which is known as Kolmogorov's 0-1 law. Now, as we have already seen in case of Borel's 0-1 law, that it is related with the convergence of some events or some limit of some sequence of events in some sense. Kolmogorov's 0-1 law is a nice result relating to what is known as a tail sigma field. So we already know that the definition and the concept of sigma field. Here we are going to define this tail sigma field, which plays a very important role in probability theory. And the beauty is that if we can show one particular event that belongs to tail sigma field, which we call actually tail event, or a particular measurable function which is measurable with respect to this tail sigma field, because it is a sigma field, it can immediately show that the probability using this Kolmogorov 0-1 law, that the probability will be either 0 or 1. So our search for or the calculation of probability almost ends there. We know that either it is 0 or it is 1. Now whether it is exactly 0 or whether it is 1, that's a different question. But for the moment we will try to define this tail sigma field, tail event, tail functions, and accordingly the Kolmogorov 0-1 law, obviously stating clearly the assumptions under which this Kolmogorov 0-1 law can hold. So we are going to describe this and state and prove this Kolmogorov 0-1 law in a very, very rigorous manner. Before stating this famous Kolmogorov 0-1 law in probability theory, let me first introduce the famous Russian probabilist A.N. Kolmogorov. He is probably one of the best probabilists in the history, and as you all know that he laid some of the foundations in probability theory. Before describing again this law, let me introduce a few concepts which are already known to you, but just a recap. Let xn n equals to 1, 2 and so on be a sequence of random variables defined on a probability space, which is omega, script f and p, where omega is the sample space, whole space, script f is the sigma field generated by the class of subsets of omega, and capital P is the probability function defined on omega and script f. Now we define one important thing which is known as tail sigma field. As we know that how to define a Borel sigma field generated by a random variable. So let us consider a sequence of random variables, or rather xm, when m is greater than equals to n, and capital B, script b is the sigma field generated by all such random variables. That means xn, xn plus 1 and so on. Consider intersection of those Borel sigma fields as intersection n equals to 1 to infinity, and this is nothing but limit of n goes to infinity, script b of xm m greater than equals to n. So we call this sigma field as the tail sigma field, as we know that the intersection of sigma fields is also a sigma field, so this is always a sigma field. And tail events we define, now we are going to define what is the meaning of a tail event. The set belonging to this tail sigma field are called tail events, and the functions that are measurable with respect to this tail sigma field are called tail functions. Since we are talking about a tail sigma field, naturally this would be a collection of events. So all the sets belonging to this tail sigma fields are actually are called tail events. And whenever there is a sigma field, we can always find some functions that are measurable with respect to this tail sigma field. So we call these measurable functions that are tail sigma field measurable we call them as tail functions. So now we know that tail sigma field, what is tail sigma field and what are tail events and what are tail functions. Now these three things have a major role to play in while stating and proving this Kolmogorov 0-1 law, and which in turn has an immense impact on the probability theory. We are going to discuss this one by one. One small example of this kind of tail event is nothing but the set of convergence of xn. That means if we define a convergence of a sequence of xn, the set on which it converges, this set we can say that this is a tail event. Now we will prove one very important lemma which will be used in proving this Kolmogorov 01 law. This lemma is states like this: let script x and a be a measurable space. Now remember, this lemma is with respect to any general measurable space, not necessarily probability space, but probability space is one kind of measurable space, so it is all the results hold true for probability space also. So let script x and script a be a measurable space and x1, x2, xn be a measurable. Then minus, if we consider minus xn, if we consider a plus b xn with mod a less than infinity and b greater than 0 but less than infinity, sup of n and n of xn and inf of xn, lim sup and lim inf of xn, they are all actually a measurable. It can be shown. If xj greater than minus infinity for every j, then if we define Sn as summation of xj, j equals to 1 to n, then it can be shown that this Sn is also a measurable, script a measurable. Moreover, if xn be random variables, that means if we consider, we have already mentioned x1, x2, xn, they are a measurable. Now if we consider another extra thing, that is this measurable space is a probability space, if we introduce probability function defined on this measurable space, then with respect to that space we can define a random variable, that is xn, or the sequence of random variables. Then lim sup of xn, lim inf of xn, they are also all tail functions. In fact, lim sup of Sn by n and lim inf of Sn by n, they are also tail functions. Now we will prove couple of things, not all, for this lemma. Consider y, which is lim sup of Sn by n. Now this means I can immediately write first take supremum of Sn by n greater than equals to k, and take limit j less than equals to k, where k goes to infinity, for j equals to 1, 2, 3 and so on. Now you can immediately split this Sn as x1 plus x2 plus up to xj minus 1 plus xj plus up to xn for every j equals to 1 to n. Here we have assumed that xj's are random variables. Now since they are random variables, it is natural that they are finite almost surely, that this is by the definition of random variables as n goes to infinity. Therefore, summation k equals to 1 to j minus 1 xk by n, that is the first part in this split up, goes to 0 almost surely as n goes to infinity. This means y, the way we define y, which is equals to limit j less than equals to k that goes to infinity and sup over n greater than equals to k of xj plus up to xn by n, because we have already noted that this summation x1 plus x2 plus xj minus 1 by n, this goes to 0 almost surely. So we are left with only xj plus up to xn by n for fixed j equals to 1, 2, 3 and so on. Since xj's are all random variables, so xj comma xj plus 1 up to xn, they are all this Borel set, that means the script b, or the Borel set generated by xj to xn measurable, this Borel measurable for all j equals to 1, 2 and so on, which again implies that xj plus 1 plus up to plus xn by n is also script b measurable, script b generated by xj to xn for all j equals to 1, 2, which immediately implies that if you take supremum over n equals to n greater than equals to k of the same function, that is supremum n greater than equals to k of xj plus dot dot up to xn by n is also script b measurable. And if we take inf of sup, this is naturally again script b measurable. Now inf of sup is nothing but lim sup of Sn is Borel measurable. That means again, if it is Borel measurable or the script B measurable for script B is generated by xj to xn for all j equals to 1, 2 and so on, then naturally lim sup of Sn by n is measurable with respect to their intersection. That means intersection j equals to 1 to infinity script B generated by xj to xn. Again we have already seen that intersection j equals to 1 to infinity script B of xj to xn is the tail sigma field of sequence xn n equals to 1 to infinity. So naturally from here, so that means here we get that lim sup of Sn by n is measurable with respect to this tail sigma field. So this immediately implies that lim sup of Sn by n is a tail function. Exactly similarly we can show that lim inf of Sn by n is also a tail function. So this proof of tail function is nothing but first we have to show that this particular function which we are going to show is Borel measurable with respect to many Borel script B Borel sigma fields, and then we take the intersection so that we come across the tail sigma field. And as we know that this intersection is also a sigma field, so this is always a tail sigma field measurable, that means it's a tail function. So this is the way of proving this whether a function is tail function, that means whether it is measurable with respect to the tail sigma field. Now we state this famous Kolmogorov's 0-1 law, which says that the tail sigma field of a sequence of independent random variables is equivalent to phi omega. Phi omega means that tail events of independent random variables x1, x2 and so on have either probability 0 or probability 1. That means if we define a tail event in terms of the sequence of independent random variables, this independent term is very important here. If we define tail events in terms of independent random variables, this must have probability either 0 or 1. Now which one it is going to be, that's a different issue, but Kolmogorov's 0-1 law at least says that it should be either 0 or 1. This can be interpreted in another way. It's a nice interpretation. Since this tail events has probability 0 or 1, or rather the tail function, we can define the tail function of independent random variables are constants, that is degenerate. So this is another interpretation of Kolmogorov's 0-1 law. Now to prove Kolmogorov's 0-1 law, we actually need two lemmas. Now we are going to state these two lemmas. Again, we have already mentioned in previous lectures. Lemma 1 states that if the random variables xt, small t belongs to capital T are independent, and T1, capital T1 and capital T2 are non-empty disjoint subsets of capital T, then script B, that is Borel sigma field generated by xt, T belongs to capital T1, and script B generated by xt, T belongs to capital T2 are independent. Another lemma, which is due to Dynkin's pi lambda lemma, let script D be a pi lambda system and G be a non-empty class of subsets of omega. If script D and G are independent, script D and script G are independent, then script B of G, that is Borel sigma field generated by script G and G, are also independent. So these two lemmas has very important role to play in proving Kolmogorov's 0-1 law. Now by lemma 1, it is immediately clear that script B generated by xk when k goes to 1 to n and script B generated by xm, m is greater than n, are independent, because we have assumed the these random variables xk are independent. So the collection up to n and Borel sigma field or script B generated by the class by the random variables up to n is completely independent of script B generated by variables after n, that is from n plus 1 onwards. This immediately implies that script B generated by x1, x2, xn and the intersection of script B generated by xm, m greater than n, where n equals to 0 to infinity, equals to tau, let's call it tau, for every n greater than equals to 1 are independent, which immediately implies that if we denote alpha by in union of n equals to 1 to infinity, script b of xk 1 less than equals to k less than equals to n, union of this first collection and tau, which is the tail sigma field, they are also independent. Now by lemma 2 we can immediately say that script b of union n equals to 1 to infinity of script b xk, k lies between 1 and n, that means actually we are taking union over n equals to 1 to infinity for all such alpha sets, and tau are independent. But what is tau? Tau is a subfamily of script b of x1, x2 and so on, which is nothing but b alpha, script b of alpha. So hence, now again script b of alpha is given by the script b of union of script b xk, k lies between 1 and n. So tau is a subfamily of script b of union n equals to 1 to infinity, script b of xk, k lies between 1 and n. So this means tau is basically independent of itself, because we have already shown this the script b of union of script b and tau are independent, but on the other hand we are showing that tau is a subfamily of script b of union of script b. That means tau is independent of itself. That means what? That if a belongs to script a belongs to tau, then if we can immediately write a equals to a intersection a. So probability of a equals to probability of a intersection a. Now a is independent of itself, so we can immediately write by the definition of independent events or probability of two independent events, we can write this is equals to probability of a into probability of a, which is equals to probability of a whole square. That means probability of a equals to probability of a square, which means probability of a should be either equals to 0 or equals to 1. So this is basically the proof of the famous Kolmogorov 0-1 law. So we have discussed Kolmogorov 0-1 law. Before that we have defined and explained the concept of tail sigma field as well as tail events and tail functions. And we have already mentioned, and it is now clear that the Kolmogorov 0-1 law, the proof of 0-1 law is slightly technical, but it's not really very difficult, but it's very interesting in giving one interesting idea, the way we get this last line, that is probability of a becomes equals to either 0 or 1. That means one event is actually independent of itself. This is a nice and interesting concept. We have not yet encountered that one before this Kolmogorov 0-1 law. And this 0-1 law actually gives us the idea and actually ensures that the probability of any tail event is either 0 or 1. Now the question that we actually mentioned at the very beginning, that whether it is 0 or 1, which one is actually true, that's entirely a different question. There might be some other theorems, other results which will answer this, that what would be the exact probability, whether it would be really 0 or 1, because Kolmogorov 0-1 law states it is either 0 or 1, it can be anything. So which one is going to be true? For that we need some other theorems that will be discussed later. But for the moment, try to understand Kolmogorov 0-1 law, which is extremely important in probability theory in deriving the probability of tail events.